Okay, linear programming then. So linear programming makes up quite a big chunk of the modelling with algorithms course for the MwA specification. There's a few approaches to linear programming that the course looks at. So the first one we're going to look at, and we're going to cover in today's video, is a graphical method to solving linear programming problems. We also need to look at something called the simplex method. Now this allows us to solve linear programming problems that are more than 3 dimensions. There is a graphical method for 3-dimensional problems, but it's not very user-friendly, so we tend to use a simplex method for 3-dimensional problems as well. We tend to just stick with graphical methods for 2-dimensional problems. So we get a simplex method. As a subset of the simplex method, we also need to cover something called two-stage simplex, which allows us to solve some problems which the simplex method can't do in its raw state, but there'll be a separate video for the simplex method. And then we also look at kind of modelling with linear programming. Linear programming often gets shortened to LP'ing. Okay, so if you see LP written anywhere, it tends to mean linear program. So modelling with LP'ing, we setting up the linear programs. It also includes kind of modelling network flows, critical path analysis, allocation problems, all with linear programming. And then also a new part of the course is something called spreadsheets or online solvers. We also deal with very big linear programming problems with kind of maybe 20 or 30 variables. We don't need to apply the simplex to that ourselves. The exam will walk through on a spreadsheet or an online solver, but we need to interpret the solution and advise. So what is a linear program? Well, a linear program is basically something that's split into 2 things. So that the first one is something called an objective function. So something that we want to either maximise or minimise. And then we have a number of constraints. So the objective function will be a function of however many variables you have. We're going to stick with 2 variables in today's video. And then the constraints are the constraints on those 2 variables. So this video is very much a theoretical one. There's no application to it, but there will be applications to other videos in this playlist. So this is quite a standard format for a linear program. We have the objective function up here. So in this case, we want to maximise this thing. Okay, so 5x plus 2y. Sometimes that's given a letter as well. So it might be given a P for profit or something maybe, or maybe a C for cost. Subject to, and then here's our constraints. So these are what we call the constraints. And these constrain the values that x and y can take. So maximise 5x plus 2y, subject to x plus y is less than or equal to 20, x plus 2y is less than or equal to 30, and 8x plus 3y is less than or equal to 20. So when we're dealing with a graphical solution to these problems, the first thing we need to do is need to graph these constraints. So to graph them, what we look to do is to write where they cross the axes. When x is 0, y is 15. When y is 0, x is 30. For a linear line, you just need to find 2 points that lie on the curve, not lie on the line. And then you can join them up with a ruler. So what I'm doing is I'm setting x to 0 and then finding where it crosses the y-axis, and then vice versa. So that gives me the 2 points where it crosses the axes. So it's easy to draw these then. When x is 0, y is 40. And when y is 0, x is 15. There we go. So those are the 2 pairs of points per inequality. Also, doing this before we do the graph actually allows us to see kind of what x and what y values we need to go up to on the axes, because quite often we're not given the scale. So we need to go up to y-axis up to 40 in the y direction, and in the x direction we need to go up to 30. So I'm going to do that and say that and that are my values of 10. Sorry, 20, so 24, sorry, it is 10. 10, 20, 30, 40, so that goes up to 40 in my y direction. And then in my x direction, I need to go up as far as 30. The scales don't have to be the same on the axes. So mine aren't going to be. That's going to be 30 there. So that's 20. And that's 10. 0. Okay. So I've got different scales on my axes, but that's fine as long as the scales are linear on both axes. And now I just join the points up. So I'm going to draw the first one. So this first constraint goes from 20 on the y-axis to 20 on the x-axis. So I'm going to go from 20 on my y to 20 on my x. So it looks like that. Join it up with a nice big long straight line. And then I'm just going to mark down here the equation of the line because that's going to be useful in a bit. So x plus y equals 20. Okay. Now I need the shading. Well, usually when we shade with inequalities on a graph, we shade the side that we want. So in this case, x plus y is less than or equal to 20. We want the underside of this line. Quick way to check that we want it. Just plug the origin in. 0 plus 0 is less than 20. So the origin is on the side of the line that I want. So I want this side. So usually I would say shade this side. But for linear programming, we actually shade the opposite way. Because if we shade the same way, the way we want for all of our inequalities, we need to look for the region that is shaded by every constraint. Whereas if we shade the way we don't want, then we are looking for the region that is not shaded at all. And that is much easier to spot. So we actually shade the side we don't want, just for linear programming. And to shade, just little flicks on the back end of the line is ample. Okay, you don't need to go overboard. You don't need to scribble all over your graph. Try and keep it nice and neat. That is adequate shading to indicate that you want this side of the line. Okay, repeat that process for the other two constraints, and we'll end up with something that looks like this. Okay, so there's my 20 to 20, there's my 15 to 30, and there's my 40 to 15. I've also put the equations of each of those lines here, here, and here, and then I've highlighted this region here, and now this region is the region that is not shaded by any of the constraints, and we refer to this region as the feasible region, or FR, feasible region. And it's feasible because every pair of values of x and y in this region satisfy the constraints. So they are a feasible solution. Not necessarily the optimal solution, but they are all feasible solutions. Now, to find our optimal solution, we now consider the objective function, 5x plus 2y. And part of the nature of linear programming is that the objective solution, the optimal solution, will lie on a vertex of the feasible region. The optimal solution will lie on a vertex of the feasible region. So I've got 5 vertices here. I've got one there, one there, one there, one there, and then the origin. So that's 5 vertices of the feasible region, and you need to check all 5. Well, you need to check these 4 definitely. This one, you can tell, won't be a maximum. But these 4 you need to check. This is why it's important to write down the equations of the lines, because I need to find the coordinates of these, these 2 points here. So I'm going to label these A, B, C, and D. So A, B, C, D. I'm also going to put E there. You don't need to include that, but I'm going to include it for completion. So A is clearly the point 0, 15. B, I'll come back to in a minute. C, I'll come back to in a minute. D is clearly the point 15, 0. And E is clearly the point 0, 0. So now to find B, we're going to solve these 2 equations simultaneously. So it equates to these 2 lines. So we get y is 10 and x is 10. And actually we can see on the graph that it looks pretty much 10, 10. But however you choose to solve them, it doesn't matter. You can use elimination, substitution, or you can even use a matrix method if you want to. I did this equation minus that to leave me with y equals 10. So B is the point 10, 10. C, now that's going to be the intersection of these two lines. To solve these simultaneously, I'm going to do that, subtract 3 times that, to get rid of my y's. So that's going to leave me with 5x is equal to 60, so therefore x must equal 12. Yeah, that looks about right on my graph. So x is 12, and y therefore would be 8. 12 plus 8 is 20. 12 times 8 is 96, plus the 24 gives you the 120. So yes, C is the point 12.8. Now that we've got those 5 points, we plug them into the objective function. So I'm going to call this P. That allows me to find the value of P. So x is 0, y is 15, gives me 30. Both 10 gives me 70. 5 times 12 is 60, plus 16 is 76. D, 5 times 15 is 75. And that's obviously 0. Let's check that again one more time. 60 plus 16 is 76. And 5 times 15 is 75. Yes, I'm happy with those. So those are my 5 objective values, and we can see that C is indeed the maximum. Okay, the objective function was to maximise, so therefore we're looking for the maximum, and the maximum is 76. Once you've established the maximum, we write the solution. So therefore x equals 12, y equals 8, and the objective function P is equal to 76. That is the solution to the linear program. We can get other types of linear program as well. So this one here is what's called a minimisation program. So we're looking to the objective function, we're looking to minimise a function rather than maximise. Okay, so it might be a minimise cost or maintenance cost or something, which an optimal would be to minimise. Again, subject to a number of constraints. So in this case we have 4 constraints. I've plotted 2 of them already. So this one goes from 625 on the x to 1250 on the y, so that's this one here. And we can see I've put the equation there as well. And then I've also plotted this one, which goes from 1000 on the x to 1000 on the y. So 1000 on the x to 1000 on the y, and again I've labelled the equation. Other 2 constraints, I've left these to show you how these are done because they're slightly different. X is greater than or equal to 200. This is going to be a vertical line. Okay, it's the line x equals 200. So x equals 200 looks like that. I'm not going to put the equation of that one because that one's fairly obvious. And we want x to be greater than 200. Therefore, we shade the left side because we don't want x to be less than 200. Don't forget, we shade the side we don't want for linear programming. To the graph y equals 2x. Because of the scales, it actually looks like y equals x, but it is y equals 2x. That's y equals 2x. And we want y to be greater than 2x, therefore we want to shade the underside of that line. And again, if you're unsure, just take a point and plug it in, try it out. Choose the point 200, 0. 200 is greater than 0, therefore it satisfies the inequality, therefore this point here is on the side of the line that we want. So therefore we shade the other side. Conversely to that, if I plug in x is 100 and y is 0, I'll get 0 is greater than 200, which is obviously not true, therefore we shade that side of the line because we don't want it. That leaves us then with this little region in here, which is the feasible region. So that's my feasible region in this case. And we can see that there are a number of vertices. So there's one there, there's one there, there's one there, there's one there. So we have 4 vertices. A, B, C, and D. And now we need to solve equations simultaneously to find the coordinates. A, B, C, and D. So A clearly has an x coordinate of 200. And it's on the line y equals 2x, so therefore y must be 400. It's nice and easy. B also has x coordinate 200, because it's on the line x equals 200. And it's this one here. If x is 200, y therefore must be 800 to make x plus y is 1,000. C is the intersection of these two lines. So that's just a little bit of effort, so I'm going to use my calculator for that one. If you haven't got one of these, get one of these. Yeah, it's a class whiz. It allows you to solve simultaneous equations. Two unknowns, amongst other things, of course. X plus y is 1,000, and 0.8x plus 0.4y is 500, and it gives you the solutions. X is 250, and y is 750. D is the intersection of this line and this line. So you've got y equals 2x. So again, I'm going to be lazy and use my equation solver. So I'm going to get 2x minus y is 0. So that's y equals 2x. And it was this line here. So 0.8x plus 0.4y equals 500. And that gives me that x is 312.5. And y is 625. Which looks about right on my graph. So now that I've got these 4 points as part of my feasible region, I plug each of those points into the objective function, which is 0.5x plus 0.25y, to give me a value of it. So, again with the calculator, now into computation mode, 200 times 0.15 plus 400 times 0.25 is 130. Change that to an 800. It's 230. 250 times 0.15 plus 0.25 times 750 is 225. And finally, 0.15 times 312.5 plus 625 times 0.25 gives me 203.125. So the minimum therefore is this one. Okay. Because this is a minimisation problem, not a maximise. So we're looking for the minimum value of the objective function, which is 130, and then we can state the solution. Therefore, x equals 200, y equals 400, and the objective function c equals 130. Thank you for watching.